The use case for the autonomous tour guide would be someone potentially with limited mobility, would be someone who wants to have some sort of robot that can pre-map an area and pre-identify all the needed landmarks within that area, allowing the user to request simple directions to reach, say, a bathroom or a particular store. So in here you can see that what we are starting with is 3 stock images of a mall. This is because we don't actually have a robot at this point that we can use to navigate and send into a place. So we're just using 3 stock images of a mall to start with. Using these, we will then run our backend against it, and we are actually looking for coffee. In this instance, we're going to run this. So this will first go through, resize all the images to one standard size, then stitch all those images together into a panoramic. And once it has finished creating the panoramic, it will then run object identification and then OCR for the optical text recognition as well. Try to identify anything it can within those images. After it has finished, it will then search whatever it found to see if it can find, in this case, coffee. If it can't find it there, it'll then go to Yelp and use Yelp instead to find the nearest match. In this case, it actually did have to go to Yelp. It says the best match business for coffee is Caldi's Coffee, which is only 8.8 meters away from our current GPS location. And it actually tells us here that this was not found in the images. So we know that this did actually come from Yelp because it could not find it within the images that we fed it. Here are the 3 original images, and here's what the 3 look like stitched together. And as you can see here, it says that the message was sent to the user's device, and the message is that the best match for the business for coffee is Caldi's Coffee. So basically send that message to the Android device at that IP address. That way it would have popped up a message for the user if they were monitoring their Android device, which presumably they are, since they requested this particular thing of coffee. And as you can see here, the amount of time it takes to stitch images together with our samples does grow linearly with the size of the images. We did samples at every 200 pixels all the way down to 200, and then we also did samples where the images were 100 pixels. And the orange line is the amount of time it took. The dotted orange line is a linear best fit to that. The blue line is the growth of the size of pixels of the images. When identifying images, we used an orb feature detection method, which is significantly faster than the comparable SIFT method. For training, we used the random forest model, and using the random forest model in 2 categories, we're able to achieve an 87.5% identification success rate. We only used 2 categories here, which was exits and bathroom images. The reason for that was just because we were having to manually gather all of the training data and testing data images from Google, and it does take quite a bit of time to do that. So we limited our training sets to what we could realistically collect. Using the Test4j Tesseract libraries for OCR optical character recognition, we used the training data that was available from the SourceForge Test4j website, and then tested against 33 of our own images with known text within them. We end up with a 9.1% success rate at reading the entire keyword that was within the image, and a 27.3% success rate reading at least part of the keyword that was within the image.